Okay, Bismillah. So today we're going to be learning about buffers, how to calculate the pH for buffers using only the Henderson isobath equation, as well as how to calculate the new pH when a strong acid is added to a buffer system. Before I start, I want to say that we're only going to be calculating pH based on the Henderson isobath equations. If you're trying to look for a different method, perhaps that your teacher wants you to learn, this video will not be able to provide that. I'm only going to be using these two equations because my professor is lenient with the method that we use as long as we get the right answer. And I personally believe that using these two equations is easy if you memorize them and know what to plug in to where. So before we start, let's talk about what a buffer is and why it is important. So a buffer is basically a system that has a stable pH because it contains a acid and a salt of the conjugate base. And if you place a strong acid into it, there's going to be minimal difference in terms of the pH. And we're going to see that when we do that later on in this video. Uh, and the example of a buffer is in your body, which includes your blood. The blood in your bloodstream is a buffer. All right, so how do we calculate the pH of a buffer? Well, we're going to use the equations. Uh, so the first one, there's going to be two cases. Either the acidic constant is given or the basidic or the basic constant is given. They're same equations, however, the pKa will be different. So if you're given the acidic constant, you're going to calculate pKa, which means I don't know what it means, but that's what you're calculating for. And if the acidic constant is given, you're going to calculate pKb. However, the method or the procedure to calculate pKa and pKb is exactly the same. The only difference is this part. So if you are given the acidic constant, then it's going to be the concentration of the conjugate base divided by the weak acid, the concentration of the weak acid. So acid will be in the denominator if the acidic constant is given. And if the basic constant is given, the conjugate acid will now be in the numerator and the base will be in the denominator. Now, every time you see a question that says buffer, remember these equations. This is what you should be thinking about when you see a question regarding buffer. Okay, so let's begin. Let's use a different color. A buffer is made by mixing 0.40 moles of HF and 0.35 moles of NaF in a 1 liter solution. Given that Ka, the acidic constant of HF, is 6.6 times 10 to the power negative 4, calculate the pH. Number one, we're given the moles of HF. Let's write it here. HF, we're given the moles and NaF. We need to convert them into molarity or concentration. Since we know that molarity, we can write it here, molarity is equal to moles divided by volume, and the volume is 1, that means the molarity is the same. So the concentration of HF is 0.4 molarity, and NaF will be 0.35 because we're just dividing by 1 liter. All right. Now, which one of these two equations are we going to use? Well, since the acidic constant is given, we're going to use the first one, which is, from what I've seen, the most common one. So we're going to have negative log of 6.6, the acidic constant, times 10 to the power negative 4. And this is our pKa plus the log of. So we're going to have the weak acid on the bottom and the conjugate base on top. The K of HF, so we have 0.4 molarity of HF, and the base 0.35. molarity. And at this point, it's just going to be plugging into your calculator and getting the answer. So we have negative log of 6.6 times 10 to the power of negative 4 plus, oops, there we go, plus log of 0.35 divided by 0.4. And you get, well, what I got is, let's erase that, 3.12. And because this is the acidic constant, this is our pH. So this is the pH. Let's verify our answer using the answer key, which is on this page. 3.12, 3.12, correct. All right, now let's move on to the second question. A solution contains, let's highlight the necessary information, 0.25 molarity of NH4Cl and 0.3 molarity of NH3. So we're giving the concentrations. We don't need to convert moles to molarity. Given that Kb is NH3 of NH3 is equal to 1.8 times 10 to the power negative 3, calculate the pH of the solution. All right, so now we're given not the acidic constant, but the basic constant. So it's going to be the same procedure. However, we're going to switch the base will be at the denominator and the acid will be in the numerator. So it's going to be negative log of 1.8 times 10 to the power negative 5 plus the log of, so the base will be at the bottom of NH3 is 0.3 and 0.25. Let me just double check. 0. Yep, okay. Now, when we calculate this, keep in mind we're not calculating pH, we're calculating P of OH. So this, when you plug it into your calculator, you're going to get P of OH. So plug it into your calculator. Uh, 0.25 divided by 0.35, 0.30. Okay, you should get, if we do, let's make it two stick face, you should get 4.7. That's your P of OH. Now we know by this law that pH plus P of OH is equal to 14. Since we calculated P of OH, we could simply do 14 minus 4.7 is equal to the pH, which is equal to, damn, that's a really ugly equal sign. 14 minus 4.7, 9.3. Oops. And this should be your pH. Let's verify our answer using the answer key. 9.34, yeah, correct. We're going to skip 3. It's the same procedure as number 1. We're giving the molarity. Let's use a different color. So we were given the molarity. We're given the molarity as well. And we're given the acidic constant. If you want to know the setup, I'm not going to solve it, but I'll show you the setup. Negative log of 4.5 times 10 to the power of negative 4 plus log of HNO2 is 0.6 and 0.45. So this is going to be your setup. And because we're given the acidic constant, we're automatically going to calculate the pH once we plug it into our calculator. So if you want to know the setup, this is the setup. And you can plug it into your calculator, and that's the answer for question 3. Now I'm going to skip to question 5 because this is where we are going to add a strong acid into a buffer. As we said, a buffer's pH is stable. It has minimal change when a strong acid is placed into it. And in question 5, we're going to prove that. I want to just say one thing. When we solve it, it's going to be a little bit different compared to what we did before. It's going to be the same equation. However, we're not going to convert moles to molarity. We're not going to convert it. We're going to keep it. We're going to keep it as moles, and I'll explain why in a bit. A buffer is made by mixing 0.3 moles of NH3 and 0.25 moles of NH4Cl in a 1 liter solution. Then 0.05 moles of HCl, which is a strong acid. Zoom out. Yeah, a strong is added. Given that the Kb, the acidic constant, is that, calculate the new pH of the solution after adding HCl. Okay, type. So first, let's begin by writing the equation like we did for question 2, negative log of the acidic constant, that's our pKb, plus log. Now, we're not going to convert it into molarity. We're not going to convert it. We're going to keep it in moles. Why? Because when we add HCl, we're adding moles into the acid and we're taking some away from the base. So base will be at the bottom. Let me read something. I'll give the NH3. So we're going to have 0.3 minus 0.05. And we're going to have 0.25 plus, because remember, acid is on the top, we're adding acid, so we're going to add a moles of acid, 0.05. And remember, because we have Kb given, we're not calculating pH directly. We are calculating P of OH. And from there, we'll calculate pH. So plug it into your calculator. And when you get a question like this, remember, I'll make a different color. Keep it in moles. That's what you want to remember. This, when you have to add a strong acid, keep it in moles. It'll make it easier for you. And you just plug it in. Negative log of 1.8 times 10 to the power of negative 5. Plus log of, I'll do this in my head, 0.30 divided by 0.25. And we calculate our pOH, which is 4.8. 4.8, we'll make it 4.82. And as I said up here, pH plus P of OH is 14. So now we can calculate P of H by doing 14 minus our P of OH, which is 4.82, is equal to our pH, which is equal to 9.18. Let's verify our answer. 9.18. Beautiful. Yeah. So this is how you calculate the new pH. Let's see how much of a difference we got after we added, before we added HCl. So let's calculate the original just for fun. Even though the question didn't ask, I'm just going to show it to you. Original pH. So the original pH, we have 1 liter, so it's going to be negative log of 1.8 times 10 to the power negative 5 plus the log of 0.25 and 0.30 is equal to OH, the original P of OH. So let's plug it into our calculator. Negative log of 1.8 times 10 to the power negative 5 plus log of 0.25 divided by 0.30. And I got, for my pOH, 4 we can make it 66. We're going to do 14 minus 4.66. Nine point 34. So as you can see, the change of our original pH is very small. It's about, let's see, 9.34 minus 9.18. Yeah, it's 0.16. So our change of pH is equal to 0.16. And this is how you calculate the pH and pOHs of buffer solutions, as well as how to calculate the new pH when a strong acid is introduced to a buffer. Thank you so much, and I hope you were able to learn buffers and pH.